the final unit we'll discuss this semester, is the control of gaseous pollutants. We'll look at incineration and we'll look at NOx reduction. So we often use oxidation systems to destroy organic chemicals that are either classified as volatile organic chemicals or they may be air toxins. We use oxidation because it's rapid. It requires oxygen and heat. So the goal of this is to convert the organics to CO2 and water. We want to produce less harmful substances. The problem is, it's not always the case. We may produce a number of incomplete combustion products. These can include chemicals like dioxin and benzofurans, both of which are extremely toxic and of significant concern when we're operating incinerators or chemical oxidation processes. H2S can be converted to SO2. We've talked about the impact of SO2 in terms both of human health effects and acid rain effects on materials and plants. Sulfur can be converted to SO2. Nitrogen-containing substances in both the fuels and in the organics that we're looking at oxidizing can be converted to both NO and NO2. Substances that contain chlorine can result in the formation of hydrochloric acid. Plastics can result in corrosion products. They can also result in causing corrosion, which will result in corrosion products. They also can result in a number of toxic organics that, if they're not removed, would be emitted into the atmosphere. And then lastly, heavy metals can be emitted in the exhaust gases. So when we look at incineration and combustion, there are three main categories of these processes: direct combustion or flaring. Remember, way back when we looked at that first lecture, we looked at the industrial accident in Mexico. It was the result of flaring or flares that went out. We have thermal incineration, and then lastly, catalytic incineration. Direct flame incineration is the method of choice when the gas stream has a heat content greater than about 3.7 megajoules per cubic meter or 99.3 BTUs per cubic foot. And we want that, or we need that heat content in order to avoid the need for supplemental fuels. The heat content is less, then we're looking at adding perhaps natural gas, propane, methane, or even landfill gas. And just to give you some comparison, when we look at natural gas, it has a heat content of about 1,000 BTUs per cubic foot. Propane is about 2,500 BTUs per cubic foot. In fact, 4% of propane is combustible. Methane, about 1,000, and landfill gas, which contains about 50% methane and 50% carbon dioxide, is about 50. So just to give you a comparison of the heat content we need from these gases versus that from these other typical fuels. Efficiencies typically about 98% or more, and it can be used for a number of processes. For instance, varnish cooking, meat smokehouse, paint, bake oven emissions. These contain significant VOCs. Meat smokehouses contain particulates, but they will also contain a significant amount of VOCs. The problem is, and this is true with all combustion processes, are the byproducts, the products of incomplete combustion. Remember, if we have complete combustion, then we produce CO2 and water if we have no other elements in the fuel. On the other hand, you will not have complete combustion, so we produce particulate matter, carbon monoxide, various different VOCs, various different polycyclic aromatic hydrocarbons, NOx, formaldehyde, organic acids, and also add in SO2. You can also produce chlorine and fluorine, depending on the sources. Direct flame incineration's the simplest of the processes that we'll look at, and it is simply a combustion chamber. So we have fuel coming in, we have the gas that we're treating, and any makeup air. We have a combustion chamber, and then we have hot gases emitted. Potentially treatment after that if it's necessary. Now, thermal incinerators or thermal oxidizers is essentially the same thing, except there is a residence chamber. So we still have a combustion chamber, but following that, we have a residence chamber. So the air passes through a flame, it's heated to its ignition temperature, where the rate of combustion is greater than the rate of heat loss. Now, in order for these to be effective, then the vapor stream must have a constant concentration of combustible gas, must have a constant flow rate. The efficiencies are higher with these, so you can achieve greater than 99%. The major factors, it's listed in both places, but the major factors are temperature, time, and turbulence, and this is the case with all combustion processes. Typically, these are run at about 1600 degrees Fahrenheit with a residence time of about 3/4 of a second, and we can achieve with that 98% reduction. On the other hand, if you wanted to look at PFAS incineration, you're looking at temperatures of about 1,000 degrees C. So you're looking at over 2,000 degrees Fahrenheit. So you're looking at much higher temperatures in order to oxidize, incinerate PFAS containing materials. Michigan, we do not have an incinerator that can incinerate PFAS containing materials, that can actually treat a waste stream at that level, at that high temperature. If you have any questions, just stop me. I'm happy to address them. So thermal incineration. We have a combustion chamber. We have turbulent mixing in there. The gas then flows from there into a reaction chamber, and this operates typically at using plug flow conditions with a velocity of about 10 to 20 feet per second, or 3 to 6 meters per second. Residence times typically from about 0.4 to 2 seconds. So very, very short residence times. In order to determine the temperature, the detention time, we need either pilot studies or literature. So you need data from the literature, pilot studies, and we also need the regulatory limits, which will guide or determine the level of removal. So we have essentially here a CSTR followed by a plug flow reactor. So we have two different flow regimes in this same unit. We can also operate these to recover heat. So you see a heat exchanger here. So rather than wasting that heat, we can use a heat exchanger in order to heat the gas to be treated. So you can see here's our gas to be treated. So what we're doing is we're using the waste heat, preheating your solvent-laden air as shown here, and then that goes into the incinerator. And this can recover somewhere between 40 to 60% of the heat, which then significantly reduces the amount of fuel that you're consuming in the thermal incinerator. In order for this to work, the airstream must have low particulate matter. The particulate matter fouls the surfaces of the heat exchanger. If it fouls the surfaces or deposits on the surfaces of the heat exchanger, that reduces the amount of heat transfer, which therefore reduces the efficiency of your heat exchanger, which means that you're not recovering that 40 to 65% of the heat that you could recover. So we do a simple problem here. We have an incinerator that's designed to destroy cyclohexane from a gas stream. The flow rate of the gas stream is 400 cubic meters per minute, and the efficiency is 99.95% that's needed based on regulatory constraints. We've determined that the rate constant, and I changed this should be cyclohexane. Read this over and missed it. So we've got a rate constant for cyclohexane at 1,000 degrees C of 3.8 inverse seconds, and you're asked to determine the volume of the reaction chamber. So we have the conditions here. We have a plug flow system. K is equal to 3.8 inverse seconds. The reaction can be described as 0, first, or second order. So based on K is equal to 3.8 inverse seconds, it's inverse time. So do we have a 0, first, or second order reaction? Anyone else? Anyone want to agree with Paige? Paige is correct. It is a first order reaction. So if we have a first order reaction and it's plug flow, we can use the equation ln C over C naught is equal to minus KT to describe the reaction of the contaminant in the chamber. So we have 99.95% removal. So C effluent is equal to, how do we know it's first order? We know it's first order because it's inverse time. So whenever you have a reaction rate constant that's inverse time, it will be first order. If it's second order, so if we have second order, then it's dC dt is equal to minus K, and I'm just going to write this as a second order in C. There, K will be, it'll still be inverse time, but it'll be, for instance, liters per mole per time. So if we have K in units of inverse concentration per time, then it's second order. If it's zero order, then it's dC dt is equal to minus K, and I'll write that C0. C0 is 1. So now it's going to be concentration per time as our units. So if we have concentration per time, it's zero order. So by looking at the units on your rate constant, it tells you whether it's zero, first, or second order. It's a really good question. Does that help? Awesome. Okay, so C effluent. If we have 99.995% removal, then my C effluent can be determined from that. So C effluent over C naught is equal to 1 minus 0.9995, or it would be 0.05%. So that's what's leaving. So ln of C effluent over C naught is ln of 0.0005. That is equal to minus KT, 3.8 seconds, times T, minus there, and T is equal, trying to get rid of the lines. T is equal to 2.8 seconds. How do I determine volume? So I have time. How do I determine volume? Flow rate times time is volume. So I have 400 meters cubed per minute times 60 seconds per minute times 2 seconds, and that is equal to 13.3 meters cubed. So I need a incinerator with a reaction volume of 13.3 cubic meters. And I just realized I didn't turn on the recording, the transcript. I apologize. Any questions? It's a little review of mass balance or reactors. If this were a CSTR, how would the reactions vary? Or how would our equation vary? It's just if it were a CSTR, it's not. What would my mass balance look like? I'm just adding this in as a review. Change in mass with respect to time is equal to my mass rate in minus my mass rate out minus my mass reacted. And if you remember, this would be Q times C in minus Q times C out minus K times C out times the volume of the reactor. And if the system is at steady state, what does that mean? Decided to throw a little review in here. If the system is at steady state, what does that mean? Exactly, no accumulation of mass, and this is equal to 0. I wrote this in terms of C out, so that means C out is equal to C in the reactor. What assumption have I just made right here? Actually, told it. What allows me to make the statement that C out is equal to C in the reactor? Steady state allows me to say that the change in mass with respect to time is equal to 0. Conservative would allow me to make the assumption that there is no reaction, that K is equal to 0. If I have perfect mixing of CSTR, then C out is equal to C reactor. If you remember nothing from the course, try and remember that. What it means for a system, for a reactant to be conservative, what steady state means, and what CSTR means. Closed system means that we can write a mass balance. Okay. If we had an open system, we'd be losing mass somewhere, and the equation is no longer valid. Does that make sense? I wasn't planning on putting that in, but I decided since we're talking about plug flow, it's the end of the semester, it's the end of the course. It's something that I think is really, really important to remember and to understand. And for those of you that will be taking 483 in the fall, you're going to see this again. The third type of oxidation systems that we use are catalytic incinerators. These are basically thermal incinerators with the catalyst. That's the difference. So you can see these become more and more complex. For some chemicals, oxidation is too slow under normal conditions, but if we add an active material, a catalyst, we can oxidize that chemical. We can also oxidize it at lower temperatures, so that reduces fuel combustion. These are best suited for low VOC concentrations and low particulate matter. And that's because the particulate matter can deposit on the surfaces of the catalyst that fouls the catalyst, and they no longer are effective. The biggest problem with these are right here. Catalysts can be poisoned, and they can be poisoned by a number of different chemicals. So for example, if there's a metal oxide catalyst, the presence of chlorinated VOCs. So for instance, let's say you're looking at a system where you have groundwater contaminated by a combination of gasoline and dry cleaning solvents, trichloroethylene, tetrachloroethylene. So you've got both compounds like benzene, toluene, ethylbenzene, and you have chlorinated solvents. And you're proposing to use a stripping column, the absorption, to transfer those chemicals from the groundwater into the air phase, and then use a catalytic incinerator in order to oxidize those chemicals, the benzene, the toluene, the tetrachloroethylene. If you use a metal oxide catalyst, it'll work for a while. It'll work for the benzene, toluene, but those chlorinated organics will poison the metal oxide so that you're going to lose significant efficiency. So you can't use it in that sort of combined stream there. Newer catalysts, cobalt oxide, combinations of cobalt oxides, manganese oxides, these tend to be more tolerant towards the chlorinated VOC so that they don't become poisoned. And then there's platinum-based catalysts that can be used for sulfur-containing VOCs. This poisoning is a significant problem with catalytic incineration. And here's an image of a reaction chamber for a catalytic incinerator. We still have the combustion chamber. We have to heat the gas. It then flows past the catalyst. Often we can operate these at lower temperatures, so that reduces the fuel consumption, passes over the catalytic oxidizer, and this improves oxidation. Biggest disadvantages, though, are the cost of the catalyst and, as I just mentioned, the poisoning of the catalyst, which deteriorates their performance.